Dear friends, welcome to a lecture on ring theory. Today in this lecture we shall study fundamental theorem on ring homomorphism. Before stating the fundamental theorem, I have written here a lemma. We shall first prove the lemma and then we shall state and prove the fundamental theorem on ring homomorphism, which is similar to the theorem of group homomorphism. First we shall see the lemma. Let U be an ideal of a ring R. We have studied earlier what is ideal, and also we have studied what is quotient ring. So, you should see the lectures on ideal and quotient rings. The lemma states U be an ideal of a ring R, then there is a homomorphism of R onto R by U. This is quotient ring. Defined with the help of this ideal U. We shall define a mapping between R and R by U and show that it is onto homomorphism. See, the proof can be stated like this. We have R by U is quotient ring, U is ideal, and see, this is R by U. That is A plus U, where A belongs to R. This is the quotient ring that we have studied in our previous lecture. And now we have to, the elements of R by U are of this type, cosets A plus U, and the elements of R we have denoted by A, and therefore we define a mapping phi from R to R by U by phi of A is equal to A plus U. So, every element of ring R is mapped or is related to this coset in R by U. Phi image of A is A plus U. A belongs to R. And we shall show this is a homomorphism which is also onto, and then R by U is homomorphic image of R. So, the theorem lemma can be briefly stated that R by U, this quotient ring, is a homomorphic image of the ring R. Now, we shall show this is homomorphism. For that purpose, we shall show it is having structure preserving properties, that is for addition and for multiplication. Now, that we shall state as phi is a homomorphism. And here this is homomorphism of R onto R by U with kernel U. U will be the kernel of this homomorphism. That is additional property in the lemma. First we shall prove it is a homomorphism, then we shall prove it is onto and the kernel is U. Now, for homomorphism we have the properties like this. Let A and B belongs to R, then phi of A plus B. This we have to prove is equal to phi of A plus phi of B. But by definition, what is the definition of phi? Phi of A is equal to A plus U, and therefore phi of A plus B will be A plus B plus U. A and B are in R, and this can be written as in earlier lecture we have defined the addition in quotient ring, and these are the addition of the cosets A plus U plus B plus U. This we have defined. A plus U plus B plus U is A plus B plus U, and therefore further this is what is phi of A, and this is phi of B by definition of phi, and thus this proves first structure preserving property for homomorphism. Also, now what about the second? Second is also easy to prove. Phi of AB, this is equal to, according to the definition, it is AB plus U, and again this can be written as by the product in quotient ring a plus u plus, not plus but into multiplication, and therefore here it is product a plus u into b plus u. And what is the a plus u? That is phi of a, and by definition. And what is b plus u? That will be phi of b. And thus this proves two structure preserving properties. Phi of a plus b is phi of a plus phi of b, and phi of ab is equal to phi a into phi b, and therefore phi is homomorphism. Phi is a homomorphism. Now it is easy to prove it is onto. Second, phi is onto. By definition it follows. See, to what is meaning of onto mapping? For every element in R by U, there exists a inverse image, and we consider element in R by U, that is of the form by definition a plus u. Let a plus u belongs to R by U. And what this implies? Where is a? A is in R. So this implies a belongs to R. And if a belongs to R, see, by definition phi of a is equal to a plus u, and phi of a is equal to a plus u. So thus for every element a plus u in R by U, there is a in R such that phi image of a is equal to a plus u, and that is the condition for onto mapping. So every image has inverse image, and the inverse image of a plus u, which is in R by U, is a in R. So thus phi is onto. And now what remaining is kernel u. Kernel of phi is u. That we shall prove. Kernel phi is equal to u. Let, for this purpose, let x belongs to kernel phi. So we shall write two-way implication. See what this implies and implied by definition of kernel. Kernel contains those elements whose image is 0. So phi of x is equal to 0. 0, see, phi is a mapping from R to R by U. 0 in R by U. 0 element in R by U. And we know 0 in R by U is 0 plus U. So this implies phi of x. And but you see phi of x is equal to, what is phi of x? By definition, you see here, phi of a is a plus u, and therefore phi of x will be x plus u. This implies x plus u is equal to, what is 0 in R by U? 0 plus u. And again that implies x plus u is equal to u, or this implies x is an element of u, because their sum is again u, and by closure property x must be in u. So this implies x belongs to u, and thus this can be stated as two-way implication. This implies and implied by. And what we will have, x belongs to kernel phi implies and implied by x belongs to u, means kernel phi is equal to u. Every element of kernel phi is an element of u, and vice versa, and therefore thus kernel phi is u. And this proves the lemma. So we have proved there exists a homomorphism from R to R by U, which is onto, and kernel of that homomorphism is the ideal of the ring U. So with the help of this lemma, now we shall state fundamental theorem of ring homomorphism. So this is now our next theorem, which is main theorem. Let R and R dash or R prime be rings. be two rings. And further, let phi, if phi is homomorphism from R to R dash, or it is on to, further let phi be a homomorphism of R onto R prime with kernel U. Then R prime is isomorphic. The quotient ring R by U. So this is known as fundamental theorem on ring homomorphism. As the fundamental theorem of group homomorphism, it is similar, and instead of there we have considered two groups and quotient group we have considered. Here we are considering two rings, and ideal this kernel is U is an ideal, and here R dash is isomorphic to R by U, that we shall prove. And for proving this, we shall consider the diagram. First, we shall consider these rings here. We will having three rings, R, R dash, R prime, or R, this quotient ring. So I shall draw the figure here, R, and this is R prime, and this is quotient ring R by U. And thus these are the three rings we have stated in the theorem. Now what we have to prove is this R prime is isomorphic to R by U. These two are isomorphic, that we have to prove. And therefore we have to establish a mapping which is isomorphism, and also onto isomorphism between R dash and R by U. And therefore we shall define a new mapping, and we will denote it by psi, and we shall denote this by phi. So and further what we shall consider, we will show the elements in this. Suppose R is an element in R, and this is related to an element in R dash, but the mapping is phi, so we may write the element as R dash or phi of R. And again, this is the element in R by U, and that element we shall write R plus U. A element in a quotient ring is written in this form of quotient, R plus U, and now there is a mapping psi. Now this helps us to define a mapping psi between R prime and R by U. Now we define the mapping. See, first we have phi is a, let phi from R to R prime, that is a homomorphism. Phi be homomorphism of R onto R dash. Be a homomorphism with kernel phi is equal to U. Now we define this new mapping psi with the help of this phi, and then we shall prove this new mapping psi is onto isomorphism. Define psi from this set R by U to R dash or R prime by psi of element in R by U is R plus U, and is equal to element in R prime, that is phi of R. So this we have defined. R belongs to R. So this is our new mapping, and now we shall prove this mapping. First we have to prove this mapping is well defined, and then we will prove it is 1 1 onto and homomorphism. Then it becomes onto isomorphism and the two groups becomes isomorphic, and our proof will be completed. So we shall show first thing, size well defined, and 1 1 also can be proved in the same. This is our first property of psi. So to what is meaning of well defined? See, psi is a mapping between these two sets, R by U and R dash. If you consider two equal elements in R by U, then their psi images must be equal. Then the mapping becomes well defined. So for that purpose we have to consider two elements in R by U, and two elements in R by U are of this form. These are the elements, these are the sets, and the mapping are the same we have shown in this diagram. So take two elements of such type, and that we shall consider R. Let R1 R2 belongs to R, and then what will be R1 plus U, R2 plus U will be in R by U. Then these are the two elements in R by U, and we shall suppose these are equal. Now R1 plus U equal to R2 plus U. These two are equal. So what this implies? This implies we shall shift this element on this side, and that can be written as R1 plus U negative of R2 plus U is equal to R2 plus U negative of R2 plus U will be 0, and so that is a 0, and this is further an element in R by U, and therefore this will be 0 plus U. And what this will imply? This will imply R1 minus R2 plus U. This will be R1 minus R2 plus U, and this is equal to 0 plus U. Element 0 in R by U. This is 0 in R by U. And further, so what this implies, R1 plus R2 plus U is equal to U, and that means R1 plus R1 minus R2 is in U. So this implies, or see, this is 0 plus U means U by closure property. So this is R1 minus R2 plus U is equal to U, and therefore this element is in U. R1 minus R2 belongs to U. But what is U? U is kernel of this kernel of phi, homomorphism. Phi is homomorphism with kernel U, and therefore this is in kernel. U is equal to kernel phi. And by definition of kernel, phi image of this element must be equal to 0. Phi image of 0 in R dash or R prime. And but this is equal to, so what is the phi? Phi is homomorphism, and therefore phi of R1 minus R2 is phi of R1 minus phi of R2. This implies phi of R1 minus phi of R2 is equal to 0, since phi is homomorphism. The same result holds for subtraction also, as we have the property structure preserving property for addition as well as for subtraction. And what this implies? This implies phi of R1 is equal to phi of R2. And again, what is phi of R1 by definition of this psi? Phi of R is psi of R plus U, and therefore phi of R1 is psi of R1 plus U. So this is psi of R1 plus U is equal to, and this will be psi of R2 plus U. And thus the two elements are equal, their psi images are also equal, and this proves well defined property. this proves psi is well defined. And the converse of this is this proves 1 1. If their images are equal, psi images are equal, and then inverse images, that if that implies inverse images are also equal, then the function is 1 1. And therefore we can write the double implication of this, it will hold always. So this implies and implied by, and thus we have two results at the same time. This r1 plus u is equal to r2 plus u implies psi of r1 plus u is equal to psi of r2 plus u proves psi is well defined, and its converse psi of r1 plus u is equal to psi of r2 plus u implies r1 plus u is equal to r2 plus u, that proves it is 1 1, and thus psi is 1 1 and onto. Yes, I shall write here, thus psi is well defined and onto. Now second, or this proves the first result. Second, we shall prove psi is onto, and that is easy. What is the psi? You see, psi is mapping from r by u to r dash. Take an element in r dash. Let an element in r dash, and that can be taken as r prime, belongs to r prime. And if this is an element in r prime, that element is phi image of some r. So this is an element in r prime. So this implies there is r belongs to r such that phi of r is equal to r prime. But what is phi of r? Phi of r is psi of r plus u. That is, this implies there is r belongs to r such that, or simply there is r belongs to r such that psi of r plus u is equal to r prime. And this proves that the inverse image of r prime under psi is r plus u, and therefore this shows this mapping psi is onto. So that is the meaning of onto. See, for every element in r prime, there is an element in r by u which is r plus u, and thus psi becomes onto. Now what remains is we shall have to prove, we have proved it is also only remaining to prove is psi is homomorphism, and then it becomes isomorphism. 1 1 onto homomorphism is isomorphism. So further we shall prove psi is homomorphism, and that is our third result, psi is homomorphism. For this we shall have to prove two structure preserving properties for addition and multiplication, and for this purpose first we shall consider psi of two elements, these two elements in r by u. Let r1 plus u, r2 plus u belongs to r by u. r1, r2 will be in ring R. And now see, we shall consider first property for addition, r1 plus u plus r2 plus u, and that we have to finally prove it is psi of r1 plus u plus psi of r2 plus u. That is, psi image of the addition is equal to addition of their psi images, that is structure preserving property, and this is equal to psi of by addition of these two cosets we will have this as r1 plus r2 plus u. This addition is defined as r1 plus r2 plus u. In our earlier lecture we have proved this addition is well defined. And see, what is the psi of r1 plus r2 plus u? By definition of psi, it is phi of r1 plus r2. This is by definition of psi. You refer this. And because phi is homomorphism, it preserves the addition structure, and therefore structure under addition. So it is phi of R1 plus phi of R2. The reason here is phi is homomorphism. And but what is phi of R1? Phi of R1 is, you see, psi of R1 plus u. Psi of R1 plus u, and phi of R2 is psi of R2 plus u. And thus this proves the first property for homomorphism. And now next is also we have psi of product of these two elements, R1 plus u into R2 plus u, and this is psi of, by product of two cosets, this is defined as R1 R2 plus u. And again this by definition of psi of R1 R2 plus u is phi of R. So this will be psi of R1 plus R2, and this is phi of R1 R2 by definition of psi. And again you see, so what is that is phi of R1 plus phi of R1 into R2. Phi is homomorphism, and therefore this is equal to phi of R1 into phi of R2. Phi is homomorphism. And what is phi of R1? Psi of R1 plus u, and this is psi of R2 plus u by definition of psi. And thus this proves the second property, psi of R1 plus u into psi R2 plus u is equal to psi of R1 plus u into psi of R2 plus u. And thus psi is, we have proved, it is well defined, it is 1 1 on 2 and homomorphism, and hence thus psi is well defined, 1 1 on 2 homomorphism. From this set ring R by U to R prime. R by U to R prime, and therefore these two rings are isomorphic. Hence R prime is isomorphic to quotient ring R by U, and this proves the theorem. So thus this is known as a fundamental theorem of ring homomorphism, where if there are two rings and homomorphic, if R prime is homomorphic image of R with kernel U, then that R prime is isomorphic with its quotient ring. So this is known as fundamental theorem of ring homomorphism, which we have just proved. I hope you understand this. The remaining part we will continue in our next lecture. Thank you for watching the lecture.